All right, guys. So now let's talk about the Boston example. Again, we're going to try and predict the median. So what we're going to do here is we're going to provide or look at the MDev as the response and all other predictors there. And then we're going to come down and we're going to see our trees. Now, all I'm doing is I'm doing a train test. Okay, so I'm using half the sample to train, half the sample to test. And if you come back, you'll see here's what the residual mean deviance is, 12.65. So if you can tell, this is the residual sum of squares, basically. Here's the distribution of the residual. So you can come down and you can see what this thing looks like. But you're even able to come down and see what the size of the tree is relative to the deviance. So is there a point of diminishing return? So for instance, is 4 the correct size? If we do a cross-validation tree on tree Boston, you'll see what you get. Here's what the tree looks like relative. So we come down here and we say the best is equal to 5 because that's where we saw diminishing returns. So when we come down, we say best is 5. And then we're just going to prune Boston to 5. So we only have 5 possible things. You see there's only 4 splits. 1, 2, 3, 4, resulting in 5 terminal nodes. So that's the entire idea. We have these 5 terminal nodes. Now what we can do is we can predict with it and we can see what this thing comes up with. So we're going to come down and we're going to say, okay, what's the basically correlation between what we predicted, which is y hat, and what the actuals are. Well, what you're seeing is it almost looks like a weighted least squares problem, right? What you're seeing is, well, you're predicting in this neighborhood and then in this neighborhood, but there's really high variability. But as you get up closer, you're starting to get better on the prediction accuracy. And if you want to come up with a sum of squares metric for predictions, you can. But let's look at random forest right now. And let me show you how to use bagging in the random forest package. All right? So let's say we want to bag the Boston data set and we want to come back with some variable importance. Use my training data set. The number of variables can be specified with this mtry, right? Because remember, in random forest, the difference between random forest and bagging is what? The number of variables that are attempted at each node. If you set it equal to the total number of variables that can be tested, what you're doing is you're running bagging. So we can use the same code in random forest to try bagging, right? So we don't have to use IPRED all the time. We can just use this as well. So what you're going to do is you're going to come down here and you're going to fit bag Boston. Now, this is an important idea as we move forward, and you'll understand why when we get into Spark and all those different things. But when you're looking at bag Boston, what you see is, we fit the model. Here's our mean of squared squared residuals. Here's the percentage of variance explained. So basically what you're doing is you're getting R squared metrics. Tried each variable 13 variables at each node, and you have 500 trees. You have a random forest that has regression trees only. Now, if we do predictions, here's what you start to see. Look at the difference between a tree and what happens if we just test the bagging. Look at how this looks. Here's the actual data, and here's what we get. See how it has that a better distribution around the line? And again, if you go up here and predict, here's the mean at 25. Here's a mean at 13. All right? What happens if we only run 25 trees, saving us some time? So the number of trees is 25. Well, you see we're right in that same area, right? You see we're right in that same area. But let's look at what happens if we do random forest with only 6 variables at each. We're even lower. Well, that's interesting. So what it's telling me is that randomness is picking it up, is actually helping. It's not becoming so data dependent on those splits. Well, that's interesting. We can also do an importance of this. Basically what this tells you is what variables are most important and what aren't. So if you look at this, what you're seeing is basically the percent increase in mean square error if you would remove the variable. It tells you these are most important, but the ones down here aren't very important. And this is node purity. Basically, it's a measure of how good does this fit? How important is this node? You can use these as kind of a visual metric to see, and in the Introduction to Statistical Learning text, they have a good couple of paragraphs on it, so you should take a look at that if you're interested. But let's look at how we do boosting. Now, boosting's a little bit different. We have it called GBM. GBM is gradient boosting, and we're going to use a Gaussian distribution. This tells us what the response is. It tells us it's continuous. It's a regression boost, okay? So what we're going to do is we're going to use deviance as the response and everything else as the predictor. We're going to run 5,000 trees, and we're going to say our interaction depth, or our small d, is 4, okay? And let's look at what we get from boosting. Well, boosting, here's what it gives us. If it gives us the relative influence, Okay, so this is the importance metric we have. All right, here's another piece of the relative influence. Here's what it looks like if we remove these variables. All right, so what happens there? But we're also able to come up with a prediction. So we predict, we come back, it's 11.8. If we predict again and we use this lambda, this is how we set lambda of 0.02, what you're going to see is we get back a different data set. So what we're trying to do is we're trying to tune the model. So the entire goal when you're using this is, once you get past trees, guys, there's not good plots. I mean, it can tell you how well you predict on the testing samples, but what you're really looking for is you're looking for what predicts the best. And any insights you can find, which this tells us about what variables help us predict well. So when you go into these metrics, these variable importance plots can be very beneficial to you because everybody likes a pretty picture, right? Well, what's this tell you? This tells you the RM variable in the Boston data set is extremely important. So as you're moving through this and as you're thinking about this and what you're doing and what you're seeing, this is important, okay? Because it's going to help you with your communication. But at the end of the day, you're going to try and present a model that predicts the best on outside samples, which we shouldn't just use a test train. So what you guys should do is figure out how to write this in a 5-fold cross-validation. Okay? Figure out how to do this in a 5-fold cross-validation and tell me what you get back. Tell me what you think it means. Tell me what the shrinkage parameters are. Because that's the stuff you're going to put in documentation and never talk to your client about. Or you're going to do it to show off for a second to really smack down questions. When you're presenting this stuff to a client, what you want them to do is you want them to see a pretty picture if you have it. So I'll tell people I use trees. And if we fit just a singular tree, here's what we get. But the problem is we tested like 7 models and this one wasn't very good. Instead, what we did, we still used tree-based methods, but it was a lot more complexity to it. So let me show you what variables were important in the tree because, well, it looks pretty bad. And then what you do is you step back and say, and by the way, we predicted with this accuracy. So when you're explaining these things, everybody goes, whoa, what about this? What about this? What about this? Sometimes if you show a model or go to, hey, you won't understand, you're going to get deep questions that you got to figure out. The balance in communicating this stuff is giving enough information so the client feels like they've been presented something they can use, but also giving the client something that's going to do the job at the end of the day. There's a trade between simplicity and interpretability, right? Simple models are interpretable. Complex models that can predict well aren't interpretable. So you've got to figure out that balance and you've got to figure out what's right for the different scenarios. A lot of the time it depends on the company you're working with and the people you choose to work with. So just keep that in mind as we go forward. All right, guys, let me know if you need anything. Let me know if you have any questions.